In this video, we will explain the method of filtration experiments, using examples to illustrate the equipment needed, how the experiment is performed, and what results can be obtained. There are two main methods of filtration. One is called constant flow filtration, which maintains a constant filtration flow rate to the filter. In constant flow filtration, the filter differential pressure increases as clogging progresses. It is possible to check how much liquid can flow before reaching the predetermined differential pressure, and to check the quality change of filtrate in the process of increasing differential pressure. The other is constant pressure filtration, in which the primary pressure, or filter differential pressure, is maintained at a constant level with respect to the filter. In constant pressure filtration, the filtration rate of the filter decreases as clogging progresses. It is possible to check whether a specified volume of liquid can be processed within a specified time, and to check the quality of the filtrate by changing the filtration pressure. These two filtration methods differ in the results obtained and in the equipment required. Selecting the method that best suits the conditions of use anticipated in mass production will enable effective operation of the data obtained. In this part, we will show you how to experiment with constant pressure filtration. The experimental method for constant flow filtration is introduced in a separate video. We will now explain the three steps of constant pressure filtration experiment: planning and preparation, conducting the experiment, and analyzing the results. Step 1. Planning and preparation. The first step is to consider what the purpose of the small volume filtration experiment is and what results you expect to obtain. By conducting the experiment in a well-planned manner, you can obtain a variety of information in a single experiment. When checking the quality of filtrate, it is necessary to determine what means will be used to check the quality of the filter. On the filter's manufacturing side, a particle counter is often used to check the number of particle by particle size. On the user side, it is most effective to analyze the content according to the quality control items of the product. Next, determine the filtration pressure. If the operating pressure on the mass production line is fixed or can be assumed to some extent, it is common to use that same pressure. Also, by conducting experiments using several different filtration pressure patterns for the same type of filter, it is possible to see the differences in filtration behavior. The next step is to select a test filter. A major advantage of small volume filtration experiments is that many types of filters can be tested with a small amount of liquid. The type of filter to be tested is filtration grade, shape, and size will be determined according to the purpose of the filtration experiment. Suitable filter types vary depending on the composition of various liquids, such as the concentration of insoluble matter present in the liquid to be filtered, particle size distribution, and the amount and size of the material to be removed. Therefore, we recommend that multiple types of filters be compared side by side. Information on filter types and filtration micron ratings can be found on our website. Filter size and shape are selected according to the experimental scale. We have many shapes suitable for small volume experiments, from disc type to capsule type with built-in small cartridges. If you are not sure what kind of filter to try, please feel free to contact us. The final step in the preparation process is to prepare the apparatus needed for the experiment. The apparatus shown in the image is an example of the simplest constant pressure filtration line. This type of instrumentation is required to perform filtration experiments. In a constant pressure filtration experiment, it is necessary to continuously record the filtrate mass. If you have a mass meter that can automatically output the readings to a computer, you can proceed with the experiment more efficiently. When analyzing filtrate, experiments such as particle counters and particle size analyzers are also required, according to the content of the analysis. Step 2. Filtration experiment. Before starting the filtration experiment, confirm the flow of the experiment content according to the objectives determined in 1.1 setting objectives. In a constant pressure filtration experiment, the filtrate mass is recorded at regular intervals from the start of filtration, and the filtrate is collected at arbitrary points. The The filter can be collected at various times, such as only at the initial stage of filtration, at several points at fixed processing time intervals to check for changes, or after filtration is completed and all accumulated filtrate is analyzed. Set up the system according to the purpose of the experiment. The endpoint of filtration is generally determined by the time required to pass a liquid through one type of filter or when the filtration flow rate has decreased to a certain degree. Assemble the filtration line and prepare the liquid in which the experiment will be conducted and place it in the pressurized tank. If particles in the liquid tend to precipitate, conduct the experiment while stirring the liquid with a stirrer or similar device. With valves A and B closed, pressurize the system so that the value indicated by the pressure gauge is near the experimental pressure. To compare the quality of the liquid before and after filtration, open valve B slowly and allow the liquid to flow once the line is assembled, and take a sample of the liquid before filtration. After collection, close valve B. Next, set the test filter. If the filter has an air vent, release it. Depending on the compatibility of the liquid and filter material, the test filter may have difficulty wetting the liquid with a fine filtration precision filter. In some cases, if the filter is not sufficiently wetted, the entire filter media is not used, and the original filter performance cannot be utilized. In this case, we recommend pre-wetting the filter before experimenting. Slowly open valve B to start the liquid flow. At this stage, do not open the valve all the way, but just enough to allow the liquid to flow. The first step after starting to pump liquid is to bleed air from the filter. Accurate filtration evaluation cannot be performed if air is trapped in the filter. Therefore, it is important to remove the air immediately after the start of the process. Close the air vent when the air has been purged. Depending on the liquid properties and experimental conditions, the liquid level may not come up near the air vent, and air may not be released from the air vent. In this case, open valve B further to increase the flow rate. When the air venting process is complete, slowly open valve B to its fullest. At this point, check to see if the pressure is off from the experimental pressure you just adjusted. If it is off, operate the regulator to fine-tune the filter differential pressure to the experimental pressure again. The stage at which the above operations have been completed is the starting point of filtration. Start measuring time with a stopwatch or similar device. If air cannot be vented, even with the valve fully open, close the air vent and turn the outlet side of the filter upward to release the internal air from the filtrate side. Similarly, when using a filter without an air vent, it is effective to turn the filter outlet side upward to release the air. From here, we proceed to record the mass of the filtrate and collect the filtrate at predetermined timing. After discarding a small amount of the initial filtrate flow for the purpose of flushing the entire line and removing solvent from the inside of the filter during pre-wetting, the filtrate is collected. When the endpoint of filtration set before the experiment is reached, close valve B to stop the flow and terminate filtration. If the filtrate is not collected until the liquid inside the filter has been completely pushed out, the state of the filtrate will change and the quality of the filtrate will be affected. Therefore, it is necessary to stop the filtration when the liquid is still filling the filter. After the liquid is passed through, open the air vent to release the internal pressure, and then remove the filter. When the remaining liquid in the filter is pushed out, air pressure is applied to dispose of it as waste liquid. This is the end of the constant pressure filtration experiment. If there are multiple test filters, replace the filters and repeat the same procedure. Step 3. Result analysis. Finally, an analysis of the experiment results will be presented with an experimental example. The purpose of this study is to investigate new filters that can be batch processed faster compared to the reference filter currently used in mass production. 2 types of filters are selected as candidates and small volume filtration experiments are conducted. In terms of scale conversion from the mass production line, the volume of one batch of mass production was 50 grams on the test filter scale, so we decided to perform filtration of more than 50 grams and collect filtrate around the mass meter values of 10, 30, and 50 grams. This is how the experiment was conducted, and the results recorded are organized. The yellow area in the table is a timing when the filtrate was collected, so the filtrate mass has not changed. Taking into account the amount of filtrate collected, the actual amount processed is shown in this table, and plotting each value produces a graph like this. From the graph of total filtration volume, it can be seen that test filter 1 was the fastest in processing 50 grams. Test filter 2 is at the same level as the reference filter, but the subsequent decrease in flow rate is small, suggesting that it has extra capacity. The flow rate graph shows that the test filter 1 has a higher initial flow rate than the reference filter. However, it also appears that the flow rate tends to decrease a little earlier. Test filter 2 has a lower initial flow rate than the reference filter, but is less prone to flow drop. The differential pressure trend can also be analyzed by fitting a blockage model to determine how the filter is clogged. The analysis can also be performed by fitting a blockage model to this situation. Please contact us for more detail on the blockage model analysis. When the removal performance of 1 micron particles was checked from the collected unfiltered liquid and filtrate of each filter, it was confirmed that the removal performance of test filter 1 was worse than that of the reference filter. Test filter 2 initially had the same removal performance as the reference filter and showed a small decrease in removal rate until the end of the filtration period. From these results, it appears that the desired speed up of batch processing can be achieved with test filter 1, but there is a risk that filter quality cannot be guaranteed. On the other hand, test filter 2 does not change the batch processing time, but seems to provide stable filtration due to its extra capacity. Based on the results of these low volume filtration experiments, moving on to mass scale testing will lead to more effective and efficient filter selection. We introduced the procedure for small volume filtration experiments using constant pressure filtration. How was it? ROKI Group International designs and sells small volume filtration systems like the one described in this article, and we also offer a service in which you can bring in actual liquids for filtration experiments in collaboration with us. If you are interested in small volume filtration experiments, please contact us. We look forward to hearing from you.